Welcome to lecture number 18. Last time we saw algebraic structure, a form, let's say G and some operation, and then we extended this idea to G and with two operation, right? And we saw this structure gave ring and field like structure. This gave magma, semi-group, group, abelian group, right? And this was extension of this idea. Why extension? Because this is less powerful. We cannot do all arithmetic in this structure, okay? The whole arithmetic is not possible here, but here it is possible if we extend this idea. Now, you may think, why only 2? Why not extend this operation to 3? Well, that is a legitimate question. Some operation, let's say I will use star 1, other operation is star 2, other operation is star 3. So we can extend this further, right? And we have a different kind of algebraic structure, right? And we can go on and on. This can be some set with star 1, star 2, star 3, and we can go on, and it will still be algebraic structure. Now, or the next step should be from here, why G and star? Well, we extended this to G and 2 operation, but I'm not talking about this. This is a different path going on. This is a different path. Now we are going to talk about different path here. This path. What we are going to do, we are going to put just one operation, but we are going to choose two set, G and H. Now see what is the difference between this and this. This path, here if you see this way, there is just, in every one of them there is one set, only the number of operations are changing. Here we have the same operation star, the number of set is changing, okay? The number of set is changing. So what kind of this structure is? Well, let's say we define a star as G cross H to H. Now see this kind of structure, what is this? What this operation is doing? Well, what it's doing is that it's taking an element from A, let's say A, and it's taking an element from H, right? Let's say B, and it's making an order pair, and then this star is going to act on order pair. How it will act? Well, it will act A star B, and it is going to produce another number C, and that number will be in H. See it very carefully. It means this A is acting on B, okay? A acting on B. This is a very important idea. These two elements are not coming from the same set G or same set H. Both elements are coming from different set, right? A is from G, H is from B. B is from H, A is from G, right? And this A acting on B through some operation star and is producing an element C that is in H, not in G, that is in H. So it is like a composition. A star B is A of B. It's like a function. It's like a function. A is acting on B, so it gives some element C, right? And this C will be in H, right? See it very clearly what's happening. It's an action. It's an action. A acting on B. For example, to make this clear, let's choose an example of function. F of x equal to, let's say, x square. Now what is happening? here we have f, right, f, and here we have some input, right, and the input is for now x. Now imagine this way, this f is coming from here g, this f is coming from g, and this input x is coming from h, right? So when f act on x, it is producing a function x square, a number, and that is coming from h, right? This is how it's happening. All right, so f acting on x, how it will act? Through operation star. So we can say this function f act on star and it produces f of x, right? And the value of f of x, this whole, not f for x, this whole is coming from h, right? F is from g, x is from h, but f of x is from h, right? See it very carefully. All right, now so how do we define? We said we have two set gh and some operation star, and this star is defined as g with not g with h, and producing an element in h, right? Now consider a set g. This set is it contains an operator, let's say O, okay, an operator O. Operator means it is going to act on an element. On what element? An element of set H. And let's say H contains x square, not x square, let's say x, 1 and 0, right? Now what happens? What happens is this. Let's define this operator O is a derivative operator dy dx, right? It's a derivative operator dy dx. What this derivative operator does, that it is going to act, this operator O, this operator O will act on, it is going to act on EL means element of the set H, right? It is going to act on element of H. It means operator O means dy dx. It is going to act on element of H, and it's going to produce an expression, and that expression will be in the set H. So let's take an example. So dy dx, right? We choose an element, so star is g cross h. G is d by dx because O is d by dx. Now we put a star, so here will be star, and then h, and h is, we have three elements to choose. We can choose any one of them. Let's say x, so x. So and we define star is composition, so dy derivative operator acting on this x, and we define it this way. Dy dx of x is 1. Now this is not important why it is 1, but it is 1. We defined it. Okay. Now we check, does 1 belongs to h? Well, of course, yes. Here it is 1. Now we have another combination, dy dx. This operator dy dx O acted on x. Now let's make it act on 1. So let's say dy dx acting on 1 will be dy dx of 1, and the answer is 0. Not important again why it is 0. Does it belongs to h? Well, of course, here it is 0. Now the third option will be, we checked for x, we checked for 1, now we have to check for 0. Same operation, dy dx is going to act on 0. So it will be dy dx of 0, and the answer is 0 again. Not important again why it is 0, but it is 0. We define this way. So 0 belongs to H? Of course yes. 1 belongs to H? Yes, true. True means 1. 0 belongs to H? Of course yes, true. 0 belongs to H? Of course it is true. So this structure, if we choose this structure, it satisfies this kind of structure, right? Here we can see it. All these three, we saw it. We saw here. What is this property called? Well, this, for now, this property is called closure. If you look carefully, what is closure? Closure says for all element, but it is a different kind of closure, right? It is not. What is closure? We say for all element AB that belongs to some set S, A star B should also belongs to S. This is definition of closure. But here what is happening? For all A that belongs to a set G, and this is symbol of and, for all B that belongs to set H. See, here both are coming from the same set, here both are coming from different set, from G and H. Now what happens? A star B belongs to H, not G, right? So it is a different kind of closure, okay? This closure and this closure is different, right? You can see it. Here AB belongs to S, then A star B belongs to S. Here A belongs to G, B belongs to H, different set, and then their combination belongs to H, not G. But it is closure with respect to this H, right? Not G. We are not talking about G. It is respect to H. We are interested in H, right? What happens? Now this is the legitimate question. What happens if we change this definition of a star? What if this star is defined as G cross H2, not H now, it is G? What happened then? What kind of a structure is this? Think carefully. This was action. It is action going on. This was action. See how dy dx acting on x produce some number. Dy dx acting on 1 produces some other number. Now it should not be number, it can be function too. For example here, see x is a function. Now dy dx acted on this, we got 1. So it is this set dy dx, this one, which is element of G, because G is O and O is dy dx, element of G acting on element of H, x1, 0, these are the element of H. This is element of G, this is element of H. So element of G acting on, this is action going on H produces these values 1, 0, 0, and this is element of H. So G cross H to H. So this was what our operation star was doing, right? G cross H to H. So it is an action. So this is how we can create any function, a machine. This is a machine, right? Now, why I call this a machine? We have to see it very carefully that there is action going on. There is a processor. This is the processor, and these are the data that we feed into this processor. And what is gonna happen, that this processor gonna take this data. But before that, we have to also make clear that this processor are different thing. These data are different thing. They are not same. So this processor coming from the set G, and this data coming from the set H. Now when this processor takes this input, this data, it is going to process it. This is where processing is happening. This line. It processes this input. These are the processor. We have the same processor for now. We can have a different processor. right? For now, this is a single valued processor, we can say, a single processor system, right? A monoprocessor. We have just one processor for each kind of input. It could be video, it could be photo, it could be audio, right? For all this different input, we are processing with the same device, which is this O, which is d by dx. And after this processing, we are getting here output. This is output, right? And this output is in this set H. Now, a real machine, a real kind of machine in the world, this kind of structure is not sufficient, right? This kind of machine are not sufficient. We will talk about this in a few minutes. So, not sufficient. Why? Because we have in this world different kind of data, right? We have different kind of data, and different data need a different kind of processing unit, right? We cannot process all this structure with the same processor. Well, deep down, the in the theory of computation, deep down, there is just one processor going on, right? Converting everything into 0 and 1, the list of binary number. The binary number B is a set of two elements, 0 and 1, right? So this is binary number 0 and 1. Now, it also form an algebraic structure. We have to remember this. If it does not form algebraic structure, then computer will not work. Why? The reason is simple. Let's say we have a binary number 1 1, and there is a binary number 1 and 0. Now, if we add them, right? If we add them, how do we add it? Well, we cannot add like this. 1 plus 0, 1, 1, 1, 1, 0. So the answer is 1, 0, 1. This is correct, but this is manually doing. But for now, let's do it manually. So we have got 1, 0, 1, right? Now we say dodge 1, 0, 1 belongs to this set 0, 1. Well, of course, each number 1, 0, 1 is coming from this set. 0 and 1 is nothing more than 0 and 1. We cannot add them and expect to have a number that is not in this number, in this set, right? Every operation on any two binary number, let's say a binary number is B1 and B2, you choose whatever operation you want. This operation produces another binary number B3, and it should belongs to our set B, this one. It cannot escape it. It means this set binary operation, this set B01 already satisfied closure property. A computer, a machine, a digital machine, a most weakest, we call weak machine, a dumb machine, a stupid machine, we can say. A stupid machine has only closure property. It only satisfies closureness. Okay? This machine is not powerful. Only closure means what? What kind of machine is this? Well, it is just magma. We call it magma because this machine only satisfies closureness, closure axiom. So a machine, so the minimum requirement for any digital machine is it should be closed, right? It should be closed. It cannot escape the binary number. You cannot expect to do calculation in decimal number. A computer needs on and off. It works on true and false, which is 1 and 0. You cannot go beyond this, right? Now in this next lecture, we will talk about this more carefully. For now, thank you.